Hi, I'm Charlie Stagg and I'm an Honorary Research Associate at UCL. I run a lab looking at non-invasive brain stimulation techniques for a variety of neurological and psychiatric diseases. We're working with the ultrasound team at UCL. We're very excited about the potential for ultrasound to modulate brain tissue. So one of the big challenges for neurological diseases is that the brain is a very difficult structure to get to, and it's a very difficult structure to change activity within. We've got a number of techniques we can use, like transcranial magnetic stimulation and transcranial direct current stimulation, but they can really only change activity right at the edge of the brain. There are structures right in the middle of the brain, called the deep grey matter, where a number of neurological diseases, such as Parkinson's disease, have known pathologies. We can't target those currently, so we're reduced to doing brain stimulation and doing very invasive surgeries and putting electrodes right into the middle of the brain. Ultrasound for us is very exciting because it offers a potential to change activity in those regions without doing brain surgery, and therefore might allow us to start treating these diseases. So I'm going to hand over to Ben now, who'll tell you something about the physics of ultrasound.
Hi, I'm Ben Cox. I'm a reader in biomedical acoustics, and I'm going to tell you a bit about ultrasound. So sound waves are physical modulations of the density or the pressure in a medium, and an ultrasound wave is one that's at a frequency so high that we can't hear it. And it's well known that bats use ultrasound for echolocation. In medical ultrasound, we're working at maybe 2 orders of magnitude higher than that in terms of frequency. Ultrasound imaging is well known, for example, for fetal imaging during pregnancy, but what's perhaps less well known is that ultrasound can also be used for therapy. So there are treatments available for using ultrasound to heat tissue to the point at which it gets ablated and therefore treat problems like essential tremor. In this project, we're interested in another aspect of ultrasound that's not to do with imaging, but is also not to do with ablating tissue. It's to do with modulating neural tissue. So stimulating neural tissue, for example, in the brain, using ultrasound to try and affect how the brain functions. I'm now going to hand over to Bradley Trevi, who's going to say a little bit more about the specifics of this project in that context.
Hi, my name's Bradley Trevi, and I'm an EPSRC Early Career Fellow working at UCL on ultrasound. So one of the biggest challenges with doing ultrasound in the brain is the presence of the skull. So the material properties of the skull are actually quite different to the material properties of the rest of the body. That means as the ultrasound waves travel from the transducer into the brain, they get aberrated, so they change shape. So a critical component of doing ultrasound therapies in the brain is correcting for the aberrations from the skull. But to do that, we need an accurate map of the skull. So the classical way to do this is to take a CT image of the patient, but obviously that gives you an ionizing radiation dose. So the specific thing we want to work on in this project is whether we can get a map of the skull from an ultrasound image. So we can't directly use a conventional ultrasound imaging machine to do that because the frequencies that are used and the image processing that are used doesn't enable us to get a good picture of the skull. But in this project, we're going to develop new hardware and software algorithms to allow us to get a morphological map of the skull, which we can then use to plan treatments for ultrasound therapy. So the reason why UCL is a fantastic place to undertake this project is because, well, 3 reasons. 1, UCL is a world-leading brain stimulation site, so there's lots of expertise in doing brain stimulation with other modalities. 2, we're a world leader in computational modeling of ultrasound. And 3, we've got an ongoing project to do with ultrasound neuromodulation in the brain.